All right, everybody. Very good to see everyone here today. Let's get the lecture going for this afternoon, okay? So, as you guys can see, the subject for today, we're going to be focusing on waves. Now, has anybody done waves before in any other courses? Okay, so maybe on this side of the room, okay, maybe that's just a coincidence. So, where did everybody do waves before over here? GCSE and a little bit in college. Okay, anyone else done some waves before? Yes? Okay, so maybe GCSE. And there's some people on this side. Has anyone done waves before over here? Okay, so great. So if you've done a bit of waves before, that's great. Maybe we might be seeing some things that you've seen before, but there might also be some new things. Now, if you haven't done waves before, that's absolutely great, okay, because that's sort of what we're geared up for here. Now, the people who've done waves before, did you guys like waves? How did you guys like you? Or not so much. Some people, yes. Some people, okay. Because this is an interesting thing. And what about people over here? Do you guys like waves? Not so much, or? Sorry. You hate waves. You hate waves. Wow. Why do you hate waves? What's wrong with waves? Don't understand. Okay. Don't understand. Now that's quite a common thing. So that actually kind of brings me on to my two main objectives for today, because it's something that I've noticed that when we start doing physics and we're thinking about, cars and rockets and things overtaking and energy, people tend to like that quite a bit. But when it comes to waves, some people, they kind of tend not to like them so much, okay? So something that I'd like to kind of convince you guys of today is, first of all, that waves are just unbelievably important. They just turn up again and again and again. And whichever subjects you're specializing in, waves are it's just ridiculous how important they are and where they come up all over the place. And hopefully, if you're not so keen on waves, especially if they're kind of a bit difficult to understand, hopefully, at least we can have an understandable start on waves, give them a fair go. The other thing I kind of want to say before we really kick things off properly is something else we're going to be doing this lecture is really building on concepts that we've been seeing over the semester. So, like I say, physics, it's not just neatly siloed into a different topic every week. It all kind of goes into this big pot, all gets stirred together. So we're going to be learning some new stuff about waves today, but we're going to be building on some of the concepts we've been seeing the past couple of weeks about materials and elasticity, and also some concepts that we saw before that about kinematics. And putting them all together, that's what we need to understand waves. Now you might say, well, all that stuff about, Young's modulus and stress, does that really have anything to do with waves? So we're going to be seeing the connection there today. So that's all I want to say before we kind of really kick things off. So before we get to anything about, the math of waves and all the important facts about them, I'd like to have a few slides to just convince you guys how unbelievably important and interesting waves are, and they just come up all over the place. So to start with, where are all the chemists in the audience? Where are the chemists? Okay, so I got a little something to start with for the chemists here, because waves are just unimaginably important if you're studying chemistry. And you might say, well, that doesn't sound right. Chemistry, it's all about, well, I don't know really what you guys do, but all about, mixing chemicals together and all that kind of stuff. But waves are unbelievably important for understanding atoms. So, where's the thing? Oh, it's not moving on. Here we go. Hang on. There we go. Where was I? Okay, yeah. So that's right. So waves, they're unbelievably important for understanding atoms. So who's studied a bit of atomic structure before? Okay, so we get atomic structure, you only get electrons in certain levels about the atoms. What causes this is all due to waves. So I have some really beautiful images over here of some models of where we find the electron in the hydrogen atom. So I think they're really beautiful distributions here. They're called kind of clouds of probability where we might find electrons. And as we add more energy to the system, we get really beautiful patterns over here. So as we add a bit more energy, we get some more features. And then as we get more energy, we get this really beautiful array of features here in the atomic structure. What I think is especially amazing about this is these beautiful pictures. These are all solutions to equations. So especially if you're focusing on chemistry and also physics, you're going to learn what these equations are, and you're going to learn how these beautiful distributions are solutions to these equations. So often when we think about equations and we think about the solution, we think, oh, it's going to be, x equals 12, or, some value like that, or the solution is going to be some speed, it's going to equal, 15 meters a second, something like that. We don't often think about the solutions to equations as being beautiful pictures like this. But when you guys learn a bit more about waves, you're going to see what the equations are and how these distributions are solutions to them. If you want to have a bit of a play around with these yourself, these images are all from a really fantastic web app. You can just open them right up on your browser here. There's a filestad.com hydrogen atom applet. So you can play around with it yourself, add some energy. It really is a lot of fun. I'll put a link to this in the recording if you want to find it there. But it really is a lot of fun to play around with. So that's where we see waves appearing in atoms. Another huge area where we see waves appearing, it's actually in data analysis and data compression. So even if you're not a chemist, you're not interested in atoms, essentially everybody is going to be working with data and working with data compression. And it's amazing how important waves are when it comes to data. So I've got this example here of MP3 compression. Does anybody ever have like an actual MP3 player? I guess no. Oh, you actually did have which one did you have? You found it in a drawer in your kitchen. See, I remember when MP3 players were like the cool new thing, and now you just find it lying around in a drawer. Does anyone else actually ever had a physical MP3 player? Okay, which one do you have, an iPod or something? You can't even remember. But you guys know what I'm talking about, right? Like the box, and you plug your headphones in when you still had to plug headphones in. Geez, it sounds so ancient now. And you get your tunes, and now it all just kind of comes out of your phone. You don't even think about it. But the point was that in order back then, especially when you couldn't have so much storage on your gizmos, if you wanted to fit hundreds or thousands of songs onto something that fitted in your pocket, you had to compress the data. And the way that was done is with MP3 compression and really understanding the data, how it's built up from waves. That's what you need to compress that sound and get it into something where you could carry all that music around with you. Now, even if obviously no one is really kind of carrying around MP3 players and it's all just, streamed over your phone or whatever, but especially when you're streaming, data compression and understanding how you can build sound out of waves, it's what makes this whole business possible. We just take it for granted now that you can pull out your phone and you can dial up any piece of music that's ever been recorded and listen to it instantly. But that's only possible because the sound has been compressed by understanding the wave. So even if it's not compressed into MP3, it will be some other format. Now, when it comes to compressing sound, it kind of seems quite natural that, maybe waves, we know wave sound is a wave, that it kind of makes sense that you're going to want to deal with waves to compress sound. But waves just turn up all over the place for data compression. And we actually use waves to compress images. Now that might sound a bit counterintuitive because, an image, it doesn't look very wavy. How many of you guys have heard of JPEG as an image format? Okay, so most all of you, okay. So JPEG image compression. So it really reduces the file size of images, but it all depends on waves. So I've got just a little picture here of how it works. So the way JPEG image compression works is instead of saving all the data for every pixel, it splits the image up into a kind of map of a little grid of pixels, and it actually saves what are called basis functions. So these are little tiny waves, and it puts the picture together based up from all these little basis functions. And by doing that, you save a huge amount of data, and that's one of the reasons why you can get images very quickly over the internet. So that's basically what's going on with JPEG image compression. And even if you're using a different image file, it's basically kind of doing something like this. So by thinking about how even images are made out of waves, it's just tremendously important. Every day, every time you use image compression, you're actually relying on an understanding of waves. So waves, they're just unbelievably important for data compression. I've not even mentioned data analysis yet. So really, our whole kind of digital technology, our whole modern world, it's just absolutely essential to understand waves. Moving up in scale, just another example of where we might find waves. One of my kind of personal favorites is we need waves in order to understand the sun. So this might not look too much like a picture of the sun, but this is actually a model of the physics going on in the sun. And these color-coded patches you can see over here are pressure waves that we get traveling through the sun. And by modeling these waves, it's absolutely essential to understand the physics of what's going on in the sun and to understand, the star that powers our home planet. So where's the environmental sciences people? Okay. Oh, just the one of you today. Okay, all right then. Well, if you're doing environmental science, this kind of business of understanding certainly waves in the sun or in our own planet, it's absolutely essential to understand planetary systems. So it's super important there. Is anybody interested in astrophysics, anything like that? Okay, so again, this is our own star, but there's just so many astrophysical examples of where we can only understand astrophysical phenomena by understanding the waves traveling through them. The last picture I'd like to share with you guys about why waves are just so unbelievably important. It's my own personal favorite. I've kind of saved my favorite to last. I'll show you guys what the picture is. Let's see what we think about this. Has anybody seen a picture like this before? Okay, a few people. So you want to tell us what's all about that? The whole universe, yeah? Our universe. Any other cosmic backgrounds? Yeah, all good stuff. And cosmic background. Great. So it sounds like some of you guys have seen this before. So if you haven't seen this before, what this really is it's a map of the entire sky. So obviously the sky, it's really, all around us, and it's just projected onto this ellipse. The same way that you might project the world onto a map of the globe, you have a certain projection. So this is a picture of the whole sky, but it's taken with a thermal camera. So those red patches are hotter and the blue patches are cooler. Now it is taken with a thermal camera. We're going to learn a bit more about the physics that goes on with thermal cameras in a bit. But essentially this is a picture of the very early universe. So the light which has made up this picture has been traveling towards us for almost the entire age of the universe. So about 380,000 years after the Big Bang. And the way we understand this picture and use this image to understand our universe, understand the ingredients of our universe, understand the physics of our universe, is by understanding how this picture is made out of waves. So can you guys see that, we've kind of got red blotches and blue blotches, and they're all kind of roughly about the same kind of size? So that's caused by some of the very earliest waves in the very earliest universe traveling through plasma in the early universe. That's what caused these features, and we can understand it by understanding waves. Now, with every single one of these examples, you could easily deliver, a whole semester lecture course on all of them. So we really are just very, very gently scratching the surface of all of them. But the point that I'd like you guys to take away from this is that from the smallest atomic scales to understanding the entire universe and everything in between, waves are just unbelievably important. They just come up again and again and again. So if you have done waves before and you kind of weren't so keen on them, just remember they are kind of unbelievably important. And if this is the first time you're seeing waves, hopefully we'll try and make sure there's not kind of too much confusion as we go along, because I think that can also put people off waves a bit. So that's all I want to share with some places where we might find waves. So I'd like to kind of get thinking a bit more about the physics kicked off today by just repeating that question that we had at the end of the last lecture, because we had that situation where we had a spring and there was a mass on it and we exert a force and we were figuring out the acceleration. Now that might not seem immediately obvious that there's a connection there to waves. So I'd like to start by recapping that question and then we can take a look at the connection to waves. So here's the question again from last time. So we have Hooke's law there, force is equal to minus kx. Now that doesn't look obviously kind of particularly wavy, does it? But remember that if we have some mass, that's going to equal to mass times acceleration. Let's see what our acceleration is. Okay, so I'll get the question going. Let's see what everybody thinks for this question. So if you're not sure about this one, you don't need to guess at all. We know that that force is going to equal our mass times our acceleration, and then we're just solving for the acceleration. So just a bit of algebra there, just rearranging the equation. All right, let's see what everybody gets for this one. What's the acceleration of our mass on a spring? Okay, so looks like most people going for option A there. So when we set that minus kx equal to ma, we just need to divide by the m, then we've solved for a. And as looks like most people got, we get our acceleration is equal to minus k over m times x. So that's the correct option there. So very well done, everybody who gave that question a go. Now, this might seem like quite an unassuming equation, might not seem like too much of a big deal, but this is actually a really important equation because it what gives rise to wave behavior. So if we take a look at what's going on there, we've got that acceleration. Now, who's done a bit of calculus before? Has anybody done a bit of calculus? Okay, so if you've done a bit of calculus, you might be familiar with this. If you haven't done any calculus before, that's absolutely fine. I'll just kind of mark out the general points here, okay? So if we look, we've got acceleration over here. So acceleration. Now, remember that acceleration is our change in velocity divided by how long that change took. So we say it's the rate of change of velocity. And velocity is how much our position changed divided by how long that change took. So we say our velocity is the rate of change of position. So what we can do, we can actually say our acceleration, we can relate this to our position. So if we say our acceleration is related to our position, so if we have x for our position, using a bit of calculus notation, we can say it's the second derivative of position with respect to time. Now, if you haven't done calculus before, you haven't seen derivatives before, please don't worry about this. Just to kind of spell out the kind of basic idea of what's going on is if we have a position and we look at how much that changes with time, that gives us velocity. If we look at how much that changes with time, that gives us acceleration. And we can write that just with this bit of notation, this d squared by dt squared. And that just means we're looking at the rate of change of this with respect to time twice. So this is really just another way of writing acceleration, d squared by dx squared. So like I said, if you've done calculus before, this might be familiar. If you haven't done calculus before and you're a bit confused by the details, please don't worry about it. I'm just really saying that we can relate our acceleration to our position. So then we know from this bit of algebra that you guys did that our acceleration is equal to, over here, so our acceleration is equal to minus k over m times x. So I'm actually going to put a box around this equation because it's really important. Put a big old box around here. Oh wow, I missed the x off the box. It's such a big equation. Okay, I'm going to modify the box. I'm going to modify the box. There we go. I don't want to leave that out. Okay. There we go. Okay, it's such a big equation. Needed an extension to the box. Here we go. So I've got the whole equation here. So what this is saying is if we have our position and we multiply it by some constants, that's giving us back our acceleration. Has anybody seen an equation like this before? Is this something? Okay, where did you see something like this before? Okay, was that doing a bit of calculus? Okay, great. So if you haven't seen anything like this before, that is absolutely fine. But this is just telling us this same equation in a different way, that if we have something which is being acted on by a spring, so if we have some mass, the mass over here, and it's being affected by something with a spring constant, this equation actually describes the behavior of the mass on the spring. So it tells us that the position of our mass has to obey this relationship, where we also have the position over here. So they're kind of both joined up with each other. Now, when you guys study calculus, you'll find out exactly how to kind of crunch through the math and solve this equation. But without doing any calculus, we can understand what's going on here in a bit more detail by thinking about some of those kinematics concepts that we were doing a couple of months ago, by thinking about how the position over here is related to the acceleration over here. And that's one of the big takeaways for today, to see how this wave behavior comes out of this Hooke's law physics. So before we get to those questions, I thought it might be a good idea to recap a couple of those kinematics kind of questions, because we haven't seen them in a little while. So I've got this question over here. We've had some questions like this before, but just not in a while, where we have the position versus time of something, and we're thinking about what the velocity is. Now, it's really useful to recap this question, partly just to kind of build on our concepts, partly, you know, we're coming towards the end of the semester, maybe you're thinking about putting all the concepts together for the exam, but also we can then see how this concept applies when we're thinking about waves. So I'll get this question going. Let's see what everybody thinks. Which of these graphs is our velocity versus time for this situation? So these kind of questions, they can be a bit tricky, but you don't need to guess. Remember that our velocity, it's going to be the slope of this position versus time. So have a think about what the slope of the position versus time is. Have a look for which of those velocity versus time is going to give us that slope. Okay, very good. Good to see all those responses coming in. Let's see what everybody thinks for this one. Okay, looks like most people going for D. So if we take a look at what's going on with the position, initially the slope's going upwards, so we got some positive velocity, then it gets halfway and I guess they change their minds, they want to go back where they came from, and then we get a negative velocity. So as most people got, the correct velocity versus time is option D there. So very well done. Great to see everybody having a go with this question, okay? Especially if you got that it's option D. So one of the reasons that I'm so keen on thinking about these kind of principles instead of memorizing equations is because it really helps to see that connection there. So this is a connection between position versus time and velocity versus time. But remember, with this equation, we want to go from position all the way to acceleration. So let's try another example now. Same kind of idea, but now we've got velocity versus time. Let's see which of these options is going to be our acceleration versus time. So again, it's the same kind of idea as with the previous question. Remember that our acceleration is the slope of our velocity versus time graph. So have a think what the slope of the velocity versus time graph is. See if you can find an acceleration which matches that. Okay, let's have a look at the responses. Let's see what everybody gets for this one. Okay, so looks like most people going for option C. Now, these questions can be a bit tricky because here we've got our velocity and it starts off positive. It can be a bit tricky to think about what happens when our velocity goes negative. But remember, the acceleration, it's just the slope of this graph. So even though the velocity, the sign of it has gone negative, the slope doesn't change. The velocity just is constantly decreasing. So the graph, the acceleration versus time, which gives us that, as most people got there, it's option C. So very well done, everybody who gave that question a go. Now, it's always useful to kind of refresh these concepts from a few weeks ago, but it's exactly these kind of ideas which help us to understand what's going on in this situation where we have the acceleration is directly related to where our position is. Now, one of the reasons why I'm so keen on not memorizing equations and thinking more about this kind of graphical sort of approach is because it allows us to take the same approach to whatever our velocity or whatever our position versus time is. So these two situations, obviously, they don't look very wavy. We've just got our velocity changing and we've got our position changing. But the same principle applies whatever our velocity or whatever our position versus time is. So let's try in this question. So I've got something which is starting to look a bit wavy. Now you might say, well, hang on, where did this wave come from? What we're going to see how this wave fits into our picture. But for now, let's just suppose that position versus time, that nice wave we have at the top there. So let's suppose that is our position versus time. What's our velocity versus time got to be in order to give us that position versus time? I'll get the question going. You guys can have a think about it, and we'll see what everybody thinks for this one. Now, this one might seem a bit tricky because everything's wavy all over the place. There aren't any straight lines in there. But it's exactly the same principle as in the question we just saw. So take a look at what the slope is going to be at different positions. See which one of those velocity versus time is going to give us that result. All right, let's take a look at the responses. What does everybody think for this one? Okay, so looks like we've got most of the options covered there. Now, these ones can be a bit tricky, but there's no need to guess. It's exactly the same principle as before. Now, a couple of things that help with this is to look for where the velocity is 0 and also to look for what the velocity is when it starts and when it finishes. So if we look at the beginning of the graph, so it does end up being a nice wave, but to start off with, it's just increasing over there. So we know to start with that the velocity has to be positive. Now remember that the velocity is the slope of this line. So where's the velocity going to be 0? It's going to be where the curve comes to the top and then starts changing direction there. That's where the velocity is going to be 0. So if we have a look at this curve there, it's our position. So if we look at our position versus time, the velocity starts out positive, and then when we get quarter of the way across, it's 0, and then it goes negative. So as it looks like most people got there, the velocity versus time for this one is option C. So very well done, everybody, with this one, because it is a bit tricky when we're suddenly seeing everything wavy all over the place. So very well done if you gave this question a go. So what this tells us is that if our position versus time is this wave in the top picture there, then our velocity versus time is option C there. So it's another kind of wave, but just kind of looks a bit different. Now, does anybody know what kind of function we might want to use to describe our position versus time on the top there? Any thoughts about that? Oh, yeah. Yeah, it's a sine wave. Very good, okay. That's a sine wave. So if you type in any sine values and you calculate it, it's just picking out values from a wave shaped like that. What about the wave, which is our velocity versus time? Can anybody spot what kind of function is that? Oh, yeah. Cosine. Excellent. Very good. Okay. So it's a cosine. So if our position versus time is a sine wave, then our velocity versus time is a cosine wave. Okay. So just a kind of interesting thing to think about there. Now you might be able to spot what's coming next, because if that's our velocity versus time, what we really want to know is what is our acceleration versus time. So next question, exactly the same kind of idea, but I've now got that cosine wave that you guys picked out in the question before. And what we're thinking about is which of these four options is going to be our acceleration versus time. So again, even though things are all kind of wavy all over the place, it's exactly the same principle as before when our velocity versus time was a straight line. Our acceleration versus time is still going to be the slope of our velocity versus time. It's just things are changing all over the place. Another thing that might help you with this one is to look for the places where the slope is a minimum, a maximum, and 0. That can help to pick out which of these has to be the correct acceleration versus time. Okay, let's take a look at the responses. Let's see what everybody gets for this one. Okay, all right, looks like you guys are kind of getting the hang of this. Okay, well, I suppose I've given it away a bit. But yeah, if we take a look at the velocity versus time. So we start out with a positive velocity, but then it decreases as we go along. And if we take a look halfway through, our velocity is 0. If we draw a tangent there, that slope is going to be 0. So what we're looking for is an acceleration versus time, which is going to give us that. And it looks like, as most people got, the correct answer is option A. Okay, so very well done, everybody, with that. That is really great, okay, because it's the same kind of idea as when our acceleration versus time is a straight line, but it does take a bit more thinking about when they're all wavy. Now, these are actually all the pieces of the puzzle that we need to put together to really understand where waves come from. Because remember, we started with that sine wave. So what I'd like to do, last slide of the day, is put all these pieces together. So I've got the three graphs here. Let me just move the code out of the way. It just says time, but we don't really need it in the way anymore. So I just want to bring those three graphs that we saw together, and we can kind of put the puzzle together, see what's going on here. So we started out with the graph of displacement versus time, and it looked like that sine wave. And then we thought about, well, if our position versus time is a sine wave, what's our velocity going to be? And then you guys figured out that's going to be a cosine wave. So there's a direct relation between the velocity and the position. And then by looking at the slope of that cosine wave, we got the acceleration. And we got that this is the shape of the acceleration. Now, can anybody spot what's the kind of function for that acceleration there? Can anybody spot that? Minus sine, excellent, really good. Okay, so it's it's still sine, but it's just flips upside down, so it's minus sine. Now this is really interesting. This is kind of where the magic happens. So if we start with a sine wave, and then we say, well, what is the acceleration of that? It's equal to minus what it is. So what that tells us is that this position versus time, this actually obeys this big old equation that I've written down here. So if our position versus time, our x, if that's a sine wave, then if we take the slope of that and then the slope of that, so the second derivative with respect to time, that gives us back another sine wave, but negative. So we get this minus sign over here. So what that's telling us is that whenever we have a sine wave like that, this obeys this equation. So if we have a mass on a spring and we move a little bit, so I can do a little demo here with a slinky. So we saw the slinky last time, and we can think of this as, we've got some mass here and then we've got the spring. If I set the slinky moving a little bit, I give it a little displacement, the slinky starts vibrating up and down. And then if you imagine this kind of tracing out a kind of time like this, if I move it along, that's going to give us a sine wave like this. And because the acceleration of a sine wave is equal to minus the original sine wave, it obeys this equation. And that's fundamentally where waves come from. So that equation, Hooke's law, force is equal to minus kx. It might seem quite an unassuming equation, but by thinking about the force of that acting on something, that's what gives rise to all of that amazing wave behavior. Now, the last few points I'll make for today is we saw with kinematics, we had those relationships between these graphs. And what's beautiful about this is that those principles apply in exactly the same way, even though they're sine and cosines and not straight lines. So we can go from displacement to velocity or acceleration by thinking about the slope, or if you've done a bit of calculus, that's the derivative. And then if we want to go from the acceleration, we can go back to the displacement by thinking about the area under the curve. Or if you've done some calculus, that's integrating. That's what we mean by integrating. So if you have done some calculus before, you might be able to see how that works exactly if you've done some integrals and derivatives of sines and cosines. If you haven't done any calculus before, that's absolutely fine. It's just that same relationship, so the slope and the area under the graph. Exactly the same as when we were studying kinematics, but now everything is a bit wavy. So that's all I'd like to say about where waves come from for the time being. In the next lecture, we're going to be exploring wave properties, so all the kind of things which make waves such an important principle when we're thinking about things in physics. So just a reminder, we've got the workshop tomorrow afternoon. Going to be really useful to have lots of practice with all the questions. Did you guys get the email about the coursework, the extension? There's been an extension to the coursework? Okay. Well, I'll send out an announcement about that if you haven't seen it already. But just they've moved the deadline for the coursework over to Monday, so I'll send out an announcement all about that. Okay. But for now, about waves, where waves come from, that's all I want to say about that. So very well done with all those questions. Okay. And I'll see you guys tomorrow in the workshop. I'll see you guys then.